Hey everybody, welcome back to Discrete Mathematics. Today we're going to talk about proof by contradiction. It's a very powerful proof tool, and basically here's the structure of the proof. We want to prove some statement phi, so what we do is we assume not phi. So we assume that the opposite is true, then hopefully we find some contradiction with some information we have, and with that contradiction, using the same logical steps we used in the logic section, we can prove that not phi is true, which is the same thing as phi. So we're going to use this to do the next couple examples. So here's one you've probably seen in class. Show that root 2 is irrational. So this right here is going to be our phi. So this is very hard to show if you were to just do a direct proof. In fact, it would be very difficult to show a direct proof because you just say, okay, root 2 is irrational, and we'd have to have a definition for irrationality and then show it. Might be a little bit difficult. You can't do a contrapositive proof because there's no if-then statement. So we have to do contradiction. So we're going to assume that root 2 is rational. So that's the same thing as saying is not irrational. So what this means is that root 2 can be written as a fraction in lowest terms. So that's a over b, where this fraction, which we'll call ab, is in lowest terms. So this just means that there's no common factor between them except for 1. So for instance, there's no way I could reduce a over b to any lower terms. So now we can do some algebraic manipulation. So let's square both sides. So then we'll get 2 is equal to a squared over b squared. We can bring b squared to the left. So b squared is equal to a squared. And what can we claim now? Well, because a squared is equal to 2 times some other number, we know that a squared is even. And if a squared is even, well, how do we get an even number? That means that it has to be either an even times an even or an odd times an even, but because this is the same thing as saying that a times a is even, the only way that a times a is going to be even is if a is even. So we know a is even from this 2b squared is equal to a squared, so we can rewrite a as an even number. So now we can say that 2b squared is just equal to 2k squared. So 2b squared is equal to 4k squared. Okay, so now that we know this, we can just isolate b squared. So b squared is going to be equal to 2 times k squared. So what's the problem here? Well, the problem here is that now b squared is equal to 2 times some number. So we can say that b squared is even. So from that, we can use the same reasoning and figure out that b is even. So what's the problem here? Well, let's take these two pieces of information here. So we have a, which is even, divided by a b, which is even, which means that if they're both even, then we can factor out a 2. So we know this is going to be not in lowest terms. Because if the top is even and the bottom is even, then we can factor out the 2 and then we can reduce it. But in our assumption, we said that a and b was in lowest terms. So this is our psi, but here we get our not psi. So by assuming root 2 is rational, we get a contradiction. Therefore, we have concluded by contradiction that root 2 is not rational. So that concludes the proof of showing that root 2 is irrational. And again, if you're not rational, then you're just irrational. So that's something you've probably seen in class. So let's do a novel example with set theory. So this is a little bit different. I'm saying prove that A minus B intersection B minus A is equal to the empty set. So you're saying, well, I could just use set laws and I could show it like that, but the easier way is to just do a proof by contradiction. So what we're going to do is we're going to assume that, well, first I'm going to do some things here. A minus B is the same thing as A intersection B bar, and B minus A is the same thing as B intersection A bar, and that's equal to the empty set. So again, we could just do some set laws here and show the contradiction very easily, but for the sake of example, we'll show by contradiction. So what we're going to do is we're going to say, okay, well, let's assume that A intersection B bar intersection B intersection A bar is not equal to the empty set. So what this means is that there's some element X in the universe such that X is going to be in this A intersection B bar intersection B intersection A bar. So we know it's in there. So what does this mean? Well, this means that X is going to be in A intersection B bar, and X is going to be in B intersection A bar. So we can break these up further. We know that then X is going to be in A, and X is going to be in B bar. So that's the first thing here. And then we expand out the second part. So we know X is going to be in B, and X is going to be in A bar. So what do we know now? Well, if X is in B bar, then we know that X is not going to be in B. And if X is in A bar, then X is not going to be in A. But then we have a contradiction here, because X is in A, but X is also not in A. So that's one contradiction. But another one is that X is not in B, but we claim that X is in B. So if we say that this set is not empty, then we get a contradiction. Therefore, the set has to be empty. So that is a proof by contradiction, and that is the method you'll be using for solving a lot of proofs. Sometimes it's easier to do the contrapositive, but sometimes it's easier to do contradiction. So you can play around with things. Basically, you just, if you're proving a statement, so for instance, this is just a statement. So this can take the form phi. If there's no conditional, then contraposition isn't going to work. However, you then have two pretty nice ways of proving things. One is a proof by definition. So we can just use definitions. For instance, we have set laws, or we can use contradiction. And hopefully we can find something that contradicts an assumption. You have to worry about your assumption though, because sometimes it's not always easy to lay out all the conditions of your assumption. So anyways, that was proof by contradiction. You'll see this on the second midterm I wrote for Discrete Math 1, which you can find at trevtutor.com in the Discrete Math 1 section. It will be in midterm number 2, and you'll be able to find another set theory practice problem that you can do, and hopefully you'll get it right. So that's it. If you have any questions, leave them in the comments below. We also have a subreddit at reddit.com/r/trevtutor where you can ask questions there. And as always, share it with your friends if this helped you, because this might also help them. So see you next time.